Real numbers, algebraic essentials. We're going to start by just classifying real numbers. We have the natural numbers, which are 1, 2, 3, and so on. And then when we go ahead and add in the number 0, we have the whole numbers. To get the integers, what we do is we take a look at the positive and negative natural numbers and 0, -2, -1, 0, 1, 2, and so on. And then we have the set of rational numbers, and that's basically your fractions. Numbers of the form of m over n, where m and n are integers and the denominator n is never 0. And the very last of the classification is the irrational numbers. And these are the numbers that do not have a terminating or repeating decimal, numbers like pi, square root of 2, and so on. And so with the real numbers, they're kind of embedded. In other words, all the rational numbers will include the integers, all the integers will include the whole numbers, and all the whole numbers will include the natural numbers. Now the next thing we're going to do is take a look at order of operations, because whenever you do a calculation, you do follow a specific order. And so people remember the acronym, please excuse my dear Aunt Sally. And that stands for do parentheses first, and then turn to the exponents. And then moving from left to right, look at multiplying or dividing. And finally, again, moving from left to right, look at adding and subtracting. So if I was to do this calculation, I would look inside the parentheses first, and I would do the calculation. And even inside the parentheses, I do have to pause, because what I see is 1 plus 3 squared. So I have a choice. Do I add or do I apply the exponent of a 2, looking at my order of operations?
Would you do the exponent?
Exponent first. So I have 1 plus 3 squared, which is 1 plus 9. And then I'm going to go ahead and look at my parentheses, and 5 minus 1 is
4.
4, so I'll take care of that. But if you have a real eye for detail, you'll notice that the parentheses are not quite completed. I still have a set of parentheses to evaluate. What am I driving at? What's my next step going to look like?
Would you add 1 plus 9?
Which gives me what?
10.
10. So I have 6 times 10 plus 3 times 4 divided by 2. And now I'm left with just the choice of multiplying and dividing or adding and subtracting. I know which would come first.
Multiply and divide.
And we move from left to right. 6 times 10 is?
That is 60.
60.
Right.
And then I'm going to move from left to right, so I'd go ahead and do 3 times 4, which is?
Which is 12.
And 12 divided by 2 is?
Is 6.
And finally, the last thing I do is add, and I end up with?
You end up with 66.
Beautiful. Next thing we're going to look at is properties of real numbers. When we look at properties of real numbers, we'll do an example from both addition and multiplication. Commutativity just means you can interchange the order when you add. 2 plus 3 is going to give you the same result as 3 plus 2. And 2 times 3 is going to give you the same result as 3 times 2. For associativity, this gives you the right to work inside the parentheses first, and you can choose where you want the parentheses to go. I'll show you what I mean. If I go ahead and take a look at 2 plus 3 plus 4 and place parentheses around the 3 plus 4, since I'm adding all the way through, I could also go ahead and look at 2 plus 3, perform that addition first, and then add the 4. And similarly for multiplication, I can take a look at 2 times 3 times 4 in parentheses and say that would be equal to what? It would be equal to 2 times?
2 times 3.
In parentheses times?
Right, times 4.
Times 4. Distributivity just means I'm going to distribute. I'm going to move. I'm going to move a multiplier through an addition set of symbols. So if I had 2 times 3 plus 4, if I distribute the 2, that means I can take 2 times the 3 and then add to it 2 times the 4. And people draw kind of these arrows to show the distributivity that's involved. As far as my identity element is concerned, well, for my identity element, I'm looking at the element itself that gets me back to that number. So 2 plus some number is going to be 2, and that number would be what?
I'm not sure.
Yeah, 2 plus what is 2?
2 plus 0 is 2.
0 is the identity element. Beautiful. Same with multiplication. I would multiply by a number to get me back to that element. 2 times what would be 2?
2 times 1?
Very good. So there 1 would be the identity element. 0 the identity element for addition, and 1 the identity element for multiplication. Inverse means you take an element you say, yeah, like a real number, and you would add the inverse to get back to the identity element. Well, for addition, the identity element is 0. What number would I add to 2 to get me back there?
Would it be
-2?
-2?
Good. And for multiplication, I'd have to think about multiplying 2 by some number to get me back to my identity element of 1, and that number I'd multiply by is
1/2.
1/2. So the additive inverse of 2 is -2, and the multiplicative inverse of 2 is 1/2. For simplifying expressions, we are going to use our distributive property, and we're going to combine like terms. Variables with the same exponents on each term can be combined. So if I take a look at this simplification, the first thing I would do is distribute the -5 to both the y and the 4z. And all you're doing is saying to yourself, -5 times y is
-5y.
Yeah, it's almost silly to say, isn't it? And -5 times 4z is
-20z.
very good. And then minus 10x.
Right.
And when I use the phrase combine like terms, I'm saying I can combine the terms where the variables and the exponents are the same. And when you go ahead and look at this, you're saying you must be referring to the terms with what? With
With an X.
With an x. So actually what you're doing is you're saying that you can go ahead and take 2x. When you subtract 10x, you're almost looking at the distributive property in reverse. You're looking at 2 minus 10, and the x being on the outside.
Oh.
So I'm driving at what? I'm driving at the fact that my next step is to take 2x minus 10x. This will give me,
-8x.
very good, minus 5y minus 20z. There's my simplification. One last point, solving. If I solve, what I want to do is find the value of x. So I want to isolate it. So x is trapped in parentheses, so the first thing I'll do is use the distributive property to remove the parentheses. What happens when I multiply a 10 through the parentheses? I get what?
You'll get 10x plus 20 equals 30.
Beautiful. Now because I'm solving, I'm going backwards from the order of operations. Order of operations, I would multiply and then add. When you're solving, reverse it. You would look at the addition and subtraction before the multiplication and division. So to isolate x, I'm going to subtract a 20 from both sides of the equation. And if I do that, I'd have 10x plus 20, and then I would subtract a 20 from both sides of the equation. And what would that give me? That would give me 10x is equal to?
Is equal to 10.
Very good. And my last step is to take the 10 that's in front of the x and move it to the other side, is what we kind of say colloquially. But what you're going to do is divide both sides of the equation by what? By
10.
By 10. We find that x is equal to?
1.
1. Beautiful job. Thank you. Classify each number as being a natural number, 1, 2, 3, 4, and so on. A whole number, 0, 1, 2, 3, 4, and so on. An integer, -2, -1, 0, 1, 2, and then it extends both to the left and the right. A rational number, which is a number that may be expressed as a fraction or a terminating decimal. And an irrational number, which is a number that cannot be expressed as a terminating decimal or a fraction. Square root of 36 may be rewritten as the number 6. Well, 6 is a natural number. It's a whole number. It's an integer. And it may be written as a fraction, 6 over 1. So it is a natural number, whole number, integer, and rational number. For 8/3, 8/3 is a fraction, but it cannot be written as a counting number, whole number, or integer. But it is a rational number. And so I'll mark it. Square root of 73. Well, the square root of 73 is not a perfect square. So it cannot be represented as a fraction, which means that it won't be a natural number, whole number, nor integer. It's irrational. negative 6. Well, negative 6, since it's negative, won't be a natural number nor a whole number, but it is an integer. And because I can rewrite negative 6 as a fraction, negative 6 over 1, it's also a rational number. And lastly, we have 3.21, 211, 2111, 2, and it pattern continues. So this number is definitely not a natural number, a whole number, integer. But is it a rational number or an irrational number? Since this decimal expansion can't be represented as a repeating decimal, this would be an irrational number. Thank you. Use the order of operations to evaluate each of the following. We'll use parentheses first, exponents second, multiplication and division third, addition and subtraction fourth, or please excuse my dear Aunt Sally. Looking at A, we have 3 times 2 squared minus 4 times 6 plus 2, and this will be equal to, and I'll work within the parentheses first. 3 times 2 is 6, so I'll have 6 squared, minus 4 times, working within the parentheses, 6 plus 2 is 8, equals. Then I'll apply exponents next. 6 squared is 36, so I have 36 minus 4 times 8. And I want to make very sure to multiply before I subtract. So I'll go ahead and multiply 4 times 8, which is what? Which is 32, and 36 minus 32 is 4. For part B, where do we begin? Well, we have 5 squared minus 4 divided by 7, minus the square root of 11 minus 2, and we're going to have this equal to, I'm going to apply the exponents first. So I have 5 squared, which is 25. 25 minus 4 over 7, minus the square root of 11 minus 2. And then I'm going to apply the parentheses, because there are really parentheses around 25 minus 4, because you're dividing that whole piece by 7. 25 minus 4 is 21, so I have 21 over 7, minus. And I do have parentheses around 11 minus 2, even though I don't see them, because I'm taking the square root of that quantity. So I'll subtract 11 minus 2, and that's 9. Next, I'll go ahead and apply the exponent. So I have 21 over 7 minus 9 to the 1/2, or the square root of 9, which is 3. Then I'll divide before I subtract. 21 divided by 7 is 3. This gives me 3 minus 3, which is 0. In the last calculation, which seems a little bit lengthy, doesn't it? We have 7 times 5 times 3 minus 2 times the quantity of 6 minus 3 minus 4 squared, end of quantity, plus 1. This is equal to. I want to work within the parentheses first. Working from left to right, I have 7 times 15. That's 5 times 3, isn't it? Minus 2 times, and I want to work within the brackets first. So within the brackets first, I see parentheses. So I go into the innermost parentheses, which is 6 minus 3, and I subtract. Minus 4 squared plus 1. Let me make this look a little more like a square. There we go. Now I'll go ahead and apply the exponents next. So I have 7 times 15 minus 2 times 4 squared is 16, so I have 3 minus 16 plus 1. And I still have parentheses to work with, so I'll go ahead and continue to work with them. We have 7 times 15 minus 2 times, and we have 3 minus 16, which is negative 13, plus 1. Now, as I look from left to right, I'm going to multiply before I subtract or add. 7 times 15 is 105, minus, and I have 2 times negative 13, which is a negative 26, plus 1. Now I'll just work from left to right. I have 105 minus a negative, which is plus 26, plus 1. And again, adding from left to right, I have 105 plus 26. That's 131, plus 1, which is 132. Thank you. Evaluate the expression 2x plus 7 for each value of x. So for each of these values of x, I'm going to substitute them in for x, and I'll start with x equals 0. So I have 2 times 0 minus 7, and that's equal to negative 7. That was part A. For part B, I'm going to evaluate the expression at 1. That gives me 2 times 1 minus 7. That's 2 minus 7. That's negative 5. And for part C, I'll evaluate at x equals a half. That means I have 2 times a half minus 7. And 2 times a half is 1. 1 minus 7 is negative 6. Thank you. A right circular cylinder with a radius of r and a height of h has a surface area in square units given by s is equal to 2 pi r times the quantity of r plus h. And what we want to do is find the surface area of a cylinder with a radius of 6 inches and a height of 9 inches, and we want to leave the answer in terms of pi. So the first thing I'm going to do is just write down the formula for surface area which was given. That's 2 pi r times r plus h. And because they did give us the formula for surface area of a cylinder, I'm just going to substitute in the value of r in 2 locations. R is 6 inches, so it would appear here, as well as here. And then the height is what? It is 9 inches. That would appear here. So my surface area is equal to 2 pi times r, which is 6, times r plus h, which is 6 plus 9. Now it doesn't matter the order that I multiply, so 2 times 6 is 12, so I have 12 pi times 15, and again it doesn't matter the order that I multiply, so that's the same as taking 12 times 15 times pi, and it looks like my surface area is equal to 180 pi. And the units, well, units would be square inches. Thank you. Exponents and scientific notation. I want to look at rules of exponents. If I had a base like a raised to an exponent like m, I could think of maybe an example of 2 cubed. And 2 cubed is 8. But what happens if I take a to the m times a to the n? Keep the same base. What I do is I add the exponents. So for example, if I had 2 cubed times 2 to the 4th, this would be 2 to the 3 plus 4, which is 2 to the what? 2 to the
2 to the 7?
7th. And this should feel intuitively correct. 2 cubed is 2 times 2 times 2. 3 of those.
Right.
2 to the 4th is
2 times 2 times 2 times 2.
so that's another 4. And
Yes.
altogether you have how many sitting there?
Should have 7.
7 2s. That's all you're doing. If I go ahead and take a look at a to the m over a to the n, then I can just subtract the exponents, and it would be a to the m minus n. So for example, if I had 2 to the 5th all over 2 to the 3rd, I would go ahead and just take 2 to the 5 minus 3 and subtract the exponents, giving me what? Giving me 2
Squared?
squared. So imagine, use your imagination, you have 5 2's multiplied in the numerator. You have how many 2's multiplied in the denominator?
3.
So 3 of the 2's upstairs and downstairs would cancel, leaving, I'm trying to give you a hint, but how many 2's?
2.
All right. Then I can go ahead and take a to the m and raise it to the n, and when you raise an exponent to an exponent, you multiply them. And what would this look like? 2 to the 5th, and I would like to raise it to the 3rd power. So this would be the same as 2 to the what? 2 to the
5 times 3?
which is 2 to the what? 2 to the
2 to the 15th.
15th. See if I can verbalize this without writing it. I have 2 multiplied to itself how many times?
5 times.
5 times. Now how many groups of these do I have?
3 groups.
3 groups of 5 2's is how many 2's?
15.
Bravo. And then finally a to the 0 is 1, and a to the negative n is 1 over a to the n. Now once we get past rules of exponents, we want to look at things like scientific notation. So that's a number in the form of a times 10 to the n, where a is a number between 1 and 10 to include 1, not include 10. It's just the absolute value of whatever number this is, the positive value of it. And n, well, that's going to be some integer. That's going to be an integer, so it's from the numbers dot, 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 -2, -1, 0, 1, 2, dot, dot, dot. These are the allowable exponents on the 10. Now, why is scientific notation used? To put large or small numbers in a relative context for us. If you go ahead and take a look at the two numbers up there, and I said, quick, which is larger? You'd be thinking, well, gee, let me count up the zeros. Whoa.
All right.
But with scientific notation, if I go ahead and just convert each of these numbers to scientific notation, I'd be able to tell quickly which is larger. So how do you convert to scientific notation? What this notation means here is that I go ahead and grab 1.23, because 123, I'm going to now rewrite it so that I have a number between 1 and 10 to include the 1. So I go 1 decimal place past the first non-zero digit, and then write out the rest of the non-zero digits. Then I multiply by 10, and I raise it to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 10 to the 11th. That's the first number that I see. Second number that I see. Well, for the second number that I see, I'm going to go ahead and do the same thing. I'm going to place the decimal point right after the first non-zero digit. That'd be right here, wouldn't it?
Yes.
So I would write what? I'd write 3.2,
2.
and then you're going to have to count with me. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Times 10 to the what? Times 10 to the
To the 10th.
10th. So if I'm multiplying 1.23 times 10 to the 11th versus 3.2 times 10 to the 10th, now I can quickly answer which number is larger by just looking at the exponents. And which number would be larger, actually?
The
first one.
The first one, that one right there, right? Because you're looking right here at that 11 being greater than 10. Well, that's with numbers that are larger than 1. For numbers that are smaller than 1, we can convert to scientific notation too. If I said which of these two numbers is larger, same conundrum. I think that's the word, conundrum. Same conundrum. But I do the same thing. I go to the first non-zero digit. I put a decimal point right about here. So I'll write 1.21. And then I'll multiply by 10 to the negative. Negative what? Negative
3.
I have to come out to say 0, 1, 2. So I got 1, 0, 2, 0, 3 zeros, and then the 1. 10 to the negative 4. Let's look at the second number. The second number, I'm going to again place my decimal point where? Between what two numbers?
9 and 6.
9 and 6. So I would have 9.6 times 10 to the negative. And I count over to that space past the 9. And how many spots do I count? 1, 2, 3, 4. I want to say what?
5.
5. So when your numbers are less than 1, you're using negative exponents on the 10. Which number is larger? Well, again, it's the first one because you're thinking 10 to the negative 4. That's going to be a larger number than 10 to the negative 5 because that would be 0.0001 versus 0.00001. Let's go backwards. I have a number and I want to write it in scientific notation. Now, 42,000 is a special number because that's the number of ounces that the largest pumpkin ever grown was. And that comes to 2,625 pounds. That's the largest pumpkin that was ever grown. I want to convert that number, 42,000, to scientific notation. So I'm going to go ahead and place my what? Place my decimal point here. And I'll write what? I'll write
4.2.
Good. And I'll multiply by 10 to the
4.
To the 4th. Very good. Let's go backwards. 9.3 times 10 to the 7th is a special number because that in miles is the distance from the Earth to the Sun. If I want to write this in scientific notation, I would write 9.3, but then I'd move the decimal point, and I would never give you a hint, but if I did, I'd do something like that. I'd move the decimal point how many times?
7.
7 times. Very good. So let's do that. Let's go ahead and move this decimal point. 1, 2, 3, 4, 5, 6, 7. And you end up with the number what? You end up with the number. Let's see if we can go ahead and switch to pen mode now. Here and here would be commas. I want to say you end up with 93 million. And we've switched from standard notation, or from scientific notation, to standard notation. And that's the distance from the Earth to the Sun, 93 million miles. Just what you thought it was. Thank you. Write each of the following products with a single base. Do not simplify further. So we'll start with part A. We have t to the 5th times t cubed, and the base is base t. So when you multiply with the same base, then you can add the exponents. So we have t to the 5 plus 3, and that would be t to the 8th. For part B, we have negative 3 raised to the 5th times negative 3. Now here the base is negative 3, so I'll write negative 3, and I'll add the exponents, which would be a 5, from the first factor, and this exponent here is a 1, so it's 5 plus 1. Multiply with the same base, again you add the exponents. So that's negative 3 to the 6th. And so since we're writing with a single base, we're not going to simplify further, we're done. Lastly, we have 3 bases, all the same. We have x squared times x to the 5th times x cubed, but because they're all the same base, I can add the exponents. So that's x to the 2 plus 5 plus 3, and that would be x to the 10th. Thank you. Write each of the following quotients with a single base. Do not simplify further. So we start with part A, which is negative 2 to the 14th divided by negative 2 to the 9th. So when you divide with the same base, you can subtract the exponents. So we have negative 2 raised to the 14 minus 9. And that would be negative 2 to the 5th. And we do not want to simplify further, we want to write it with a single base, so we're done. For part B, we have t to the 23rd divided by t to the 15th, and again, when you divide with the same base, you can subtract the exponents, so this would be t to the 23rd minus 15, which would leave us with t to the 8th. For part C, we have z times the square root of 2, all raised to the 5th, divided by that same base, which is z times the square root of 2. So we do have similar bases here. So again, because we're dividing, we can subtract the exponents. That leaves z to the square root of 2, raised to the 5 minus 1, because the exponent on this base is really a 1. And that leaves us with z times the square root of 2 raised to the 4th, and again, because we're writing with a single base, we don't want to simplify further. We are done. Thank you. Write each of the following products with a single base. Do not simplify further. For part A, we have x squared to the 7th. So my base x is raised to the 2, and then we go ahead and raise that to the 7th. When you raise an exponent to an exponent, you can multiply the exponents. So that's x to the 2 times 7, and that's x raised to the 14th. For part B, we have 2t, it's raised to the 5th, and 2t to the 5th is cubed. So now I'm going to take my 2t raised to the 5th, and since that is raised to the 3rd, I can multiply the exponents. So I have 2t to the 5 times 3. And that would be 2t to the 15th. Because I want to write the answer with a single base and I don't want to simplify further, I'm done. For part C, well, I have negative 3 raised to the 5th, and that is raised to the 11th. So the negative 3 is raised to the 5 times 11, because I'm raising an exponent to an exponent, I can multiply them. And that leaves negative 3 to the 5 times 11, negative 3 to the 55th. And again, because I'm raising to a single base, and I don't want to simplify further, I am done. Thank you. Simplify each expression using the zero exponent rule of exponents, which just says if I have a base that's positive not equal to 1, if I raise it to the 0 power, that's equal to 1. That's my zero exponent rule for exponents. So in the first case, we have c cubed divided by c cubed. Whenever you divide with a common base, you can subtract the exponents. So I now have c raised to the 3 minus 3, which is c to the 0, and that would be 1. For part B, we have negative 3 x to the 5th divided by x to the 5th. So I want to realize that I will rewrite the negative 3, but the common base of an x is in the numerator and denominator. Since I'm dividing with a common base, I can subtract the exponents on the x only. So x is raised to the 5 minus 5. This means I have negative 3 times x to the 0. So now I have negative 3 times, and x to the 0 is just 1. And negative 3 times 1 is negative 3. On part C, I have the base of j squared times k raised to the 4th, divided by a product, j squared k times the base j squared k raised to the 3rd. Now notice I do have a common base, which is j squared k. So I'm going to leave the numerator as j squared k raised to the 4th. In the denominator, I'm multiplying by a common base of j squared k. When you multiply with a common base, you can add the exponents. That'd be 1 plus 3. So again, in the numerator, I have j squared k raised to the 4th over what? J squared k raised to the 4th. Now I'm dividing with a common base, so I can subtract the exponents. This gives me j squared k, and that base is raised to the 4 minus 4, subtracting the exponents. Well, 4 minus 4 is 0, so now I have j squared k raised to the 0. And again, if I'm raising j squared k to the 0, then the result is 1. Thank you. Simplify each of the following products as much as possible using the power of a product rule. Write the answers with positive exponents. So we'll start with A, which is a times b squared cubed. So I'll take each factor and raise it to the 3rd power. I'll take a and raise it to the 3rd power, and b squared and raise it to the 3rd power. And that leaves me with a cubed times b to the 2 times 3. And 2 times 3 is 6. For b, we have 2t raised to the 15th power. Again, I'll take each factor and raise it, in this case, to the 15th power. So this leaves me with 2 to the 15th power multiplied by t to the 15th power, which I can leave that way, or I can just evaluate 2 to the 15th. So that leaves me with 32,768 times t to the 15th. For part C, we have negative 2 w to the 3rd raised to the 3rd. Again, taking each factor, starting with negative 2, I'll raise it to the 3rd. I'll take w cubed and raise it to the 3rd. Now negative 2 times negative 2 is 4, times negative 2 is negative 8, times w, and when you have an exponent raised to an exponent, you multiply the exponents, times w to the 9th. And for part D, we have 1 over negative 7z to the 4th. So I'll go ahead and write 1 over, and again take each factor. The negative 7 is one factor, raise it to the 4th. The z is another factor, raise it to the 4th. And it turns out negative 7 to the 4th. Well, that's 2,401. So this leaves me with 1 over 2,401 times z to the 4th. Thank you. Simplify each of the following quotients as much as possible using the power of a quotient rule. write the answers with positive exponents. So the first one we have is 4 divided by z to the 11th, and that quotient is raised to the third. So first thing I'm going to do is take the numerator, which has a 4, raise it to the third, and I'll apply the denominator to the third power as well. Now, 4 to the third is 64. 4 times 4 is 16. 16 times 4 is 64. In the denominator, I have z raised to the 11 times 3. And that's because when you raise an exponent to an exponent, you can multiply the exponents. So that leaves us with 64 over z to the 33rd. For part B, we're going to take a look at p divided by q to the third, and that whole quotient is raised to the sixth. So much as I did a moment ago, I'll take my numerator, p, raise it to the sixth, and my denominator, q, which is cubed, and raise it to the sixth. So I'll rewrite p to the sixth, but in the denominator again, because I have an exponent raised to an exponent, I'll go ahead and multiply those exponents. I have 3 times 6. So in the numerator, this leaves p to the 6th, and in the denominator we have q to the 18th. For c, I have negative 1 over t squared, and that's raised to the 27th. So I'll take the negative 1, which is in my numerator, raise it to the 27th, and divide by t squared, which is in the denominator, raise it to the 27th. Now negative 1 multiplied to itself an odd number of times, well that's negative 1. And in the denominator, since I'm raising an exponent to an exponent, I'll multiply, and I have t squared to the 27th. This leaves me with a negative out front over t to the 2 times 27, which is t to the 54th. For part D, I have j cubed multiplied by k to the negative 2. And I'll raise that to the 4th. So I'll take each term that I'm multiplying here. I'll start with j cubed, raise it to the 4th, and then I'll take k to the negative 2, raise it to the 4th. Well, when I raise an exponent to an exponent, I know I'll multiply those exponents. I have j raised to the 3 times 4 times k raised to the negative 2 times 4. This leaves me with j to the 12th, 3 times 4, k to the negative 8, negative 2 times 4. And because I want to leave the answers with positive exponents, I'll rewrite the k to the negative 8th as 1 over k to the 8th. And so my answer is j to the 12th over k to the 8th. Thank you. Simplify each expression and write the answer with positive exponents only. Here we have u raised to the negative 1 times v divided by v to the negative 1, and the whole quotient is squared. So we're going to work within the parentheses first, and we'll start by writing with positive exponents. So that means if I go ahead and rewrite u to the negative 1 as a positive exponent, in the denominator it would be u to the first. I'll write the v that's in the numerator again, and then if I have 1 over w to the negative 1, if I would like to rewrite that with a positive exponent, I would put w to the first in the numerator and take off the negative, and that whole quotient is squared. Now, I do have a common base in the numerator, so with the common base I'll add the exponents. That gives me v to the 1 plus 1 in the numerator over u. Again, the whole quantity is squared. And that leaves me in the numerator v to the, well, 1 plus 1 is 2, so that's v squared over u squared. Now that I see two distinct bases, each raised to a positive exponent, I'll go ahead and apply the 2 that's on the outside of the parentheses. So when you have an exponent raised to an exponent, you can multiply those exponents. So in the numerator, we have v to the 2 times 2. And in the denominator, we have u to the first times 2. Well, 2 times 2 is 4, so this leaves us with v to the 4th all over u to the 2nd. 1 times 2 is 2. And we have 2 unique bases with positive exponents, and we're done. Thank you. Simplify each expression and write the answer with positive exponents only. We have 3w squared, all raised to the 5th, divided by 6w raised to the negative 2, all raised to the 2nd power. And our game plan is to apply the exponents that we see in the numerator as well as in the denominator. So we'll work on the numerator first. We'll take each base and raise it to the 5th. So we have 3 to the 5th, and then we have w squared raised to the 5th. And in the denominator, we'll take each base and apply it to the 2nd power. We have 6 squared, and then we have w raised to the negative 2, and that is squared. Now what we want to do is apply the exponents on 3 and 6. So we have 3 to the 5th, and 3 to the 5th is 243. In the denominator, 6 squared is 36. Let's turn our attention to the exponents. When you raise an exponent to an exponent, you can multiply. So the w in the numerator is raised to the 2 times 5, while the w in the denominator is raised to the negative 2 times 2. So let's go ahead and simplify further. In the numerator, we have 243 w to the 2 times 5, which is 10, all over 36 times w to the negative 2 times 2, which is to the negative 4. Now we want to write our answers with positive exponents only. That's what we're seeing right here. So notice we do have a negative exponent right here. So let's rewrite our expression as 243 w to the 10th, and then if I go ahead and apply the negative 4, I take the reciprocal of 1 over w to the negative 4, and that's w to the 4th in the numerator. And then I divide by 36. Almost done. The only thing left to do is to see if we can reduce the fraction, and also see if we can go ahead and take these like bases that are multiplied and turn around and add the exponents. Well, it turns out 27 times 9 is 243, while 4 times 9 is 36. And then in the numerator, when you multiply the bases, you can add exponents. So that's w to the 10 plus 4. We're now ready for the very last step. Notice the 9's do cancel, so we're left with 27 in the numerator times w to the 10 plus 4, which is w to the 14th, all over 4. Thank you. Write each number in scientific notation. Now there are 2 steps. We have 2 rather large numbers, larger than 1. So when we look at part A, the first step is to look at the numbers prior to all the zeros, and that's a 24. We put a decimal point to the right of the first non-zero integer, and we continue to write the integers until we get to the whole host of zeros. Well, that would be 2.4. Then we want to multiply by 10 to an exponent. Now the exponent is positive because the number is greater than 1, and now we just count to zeros. 3, 6, 9, 12, 15, 18, 21 zeros. So we have 21 zeros. And then we also have to realize we have a placeholder for this 4, because we turned the 4 into a 0.4. So we'd have to multiply by another 10 to do that. So that means our exponent is going to be to the 22nd power. We have 2.4 times 10 to the 22nd. Let's do this again with the number we see in part B. What do? We take a look at putting a decimal point to the right of the first non-zero number. We would have 1.3, and we would stop at 3 because that's when the host of zeros begin. Then we're going to multiply by 10 to an exponent, and we'll start by counting the zeros, won't we? We have 3, 6, 9, 12, 15, 18, and 20. We have 20 zeros, so it'll be 10 to the 20th. But notice we have a 0.3 that really should be the number 3. And so what we're going to do is we're going to add one more 0. So it's 1.3 times 10 to the 21st. Thank you. Write each number in scientific notation. There are 2 steps. The first step is to go ahead and put a decimal point to the right of the first non-zero integer. And then we multiply it by 10 to an exponent that's negative. Why is it negative? Well, the number is smaller than 1. Then what we do is painstakingly count the zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros. We have 12 zeros. But notice we also have to account for that 9 that is really after the decimal point. So we'll have to have one more placeholder. So we have 9.4 times 10 to the negative 13th. On part B, it's a very similar situation with a minor difference. First step, well, we know we place a decimal point to the right of the first non-zero integer and write the remaining integers. And in this case, it's 1.43. There are 2 integers. Then we multiply by 10 to a negative exponent because the number is what? Number is smaller than 1. We count the zeros. 1, 2, 3, 4, 5, 6. We have 6 zeros, but we need one more placeholder for the 1. So we have 1.43 times 10 to the negative 7. Thank you. Convert each number in scientific notation to standard notation. We'll start with 3.47 times 10 to the 14th. Now, because 10 to the 14th is larger than 1, we're going to have a number that is going to be huge. This tells me we're sliding our decimal point to the right. We're going to slide it 14 places. So I'll write 347. That's 2 of the 14 places, leaving 12 more places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And here's my representation in standard notation. For B, what do we have? Negative 2 times 10 to the 6th. Now, 10 to the 6th, that portion of it is greater than 1. When you multiply negative 2, now it is less than 0, but 10 to the 6th is greater than 1. So I'll slide the decimal point 6 places to the right. So I'll write negative 2, and I'll add 6 zeros. 1, 2, 3, 4, 5, 6. For part C, we have 7.91 times 10 to the negative 7. And 10 to the negative 7 means 10 is raised to a negative exponent. This portion, 10 to the negative 7, is less than 1. We now slide our decimal point to the left 7 places. When I slide the decimal point 1 place to the left, that leaves 6 more places for zeros. So I have 0.1, 2, 3, 4, 5, 6 zeros, 791. And lastly, when I have negative 8.05 times 10 to the negative 12, again, the 10 to the negative 12 portion is less than 1. We'll slide our decimal place to the left 12 places. When I slide the decimal point once to the left, I now have to add 11 more zeros. So I have negative, because the number is negative, and then I have 11 zeros. 0 point, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros. The 12th is the 8, and then 0, 5. Thank you. Perform operations and write the answer in standard notation. So we're starting with part A. We have 8.14 times 10 to the negative 7, a number written in scientific notation, and it's multiplied by another number written in scientific notation, 6.5 times 10 to the 10th. I want to write this product in scientific notation and then rewrite it in standard notation. So I'll multiply the two numbers that are not written with base 10. I'll multiply 8.14 times 6.5. And then I'll multiply that by, and I'll multiply 10 to the negative 7th by 10 to the 10th. Let's look at the first product. 8.14 times 6.5 is 52.91. I'm going to multiply by 10 to the, and when you multiply with the same base, you can add the exponents. Well, negative 7 plus 10 is 3. Now, if I'm going to write this in scientific notation, I'll slide the decimal point one spot to the left, making 5.291 the first term. That made the first term smaller, so I'll add 1 to the exponent on 10 to make the second part of the product larger. And now I'll just go ahead and slide my decimal point to the right 4 places. And I have 5, and if I slide it to the right 4 places, I have 2910, or 52,910. And for part B, again, I have these two numbers that are now being not multiplied but divided, but each number is in scientific notation. I have 1.2 times 10 to the 8th, not multiplied but divided by 9.6 times 10 to the 5th. And I'll put in my parentheses. So again, I'm going to rewrite this in scientific notation. So I'll rewrite what I have by dividing the numbers that are not written with base 10. So that would be 1.2 divided by 9.6. And I'm going to multiply and then divide the numbers that are written in base 10, the order we multiply. Well, that doesn't matter. Those operations are commutative. So I'll have 10 to the 8th divided by 10 to the 5th. Now, 1.2 divided by 9.6, that's 0.125. And I'll multiply that by 10. When you divide numbers with the same base, you subtract the exponents. 8 minus 5 is 3. It's almost written in scientific notation. I'm going to slide the decimal point one spot to the right of this first number that I see. So the point 125 becomes 1.25. I've made that number bigger. So I must compensate and make the exponent on the 10 smaller. So times 10 squared. We moved it one decimal place. Now I'll switch to my standard notation. I'll slide my decimal place 2 spaces to the right, and I have 125. Thank you. In April 2014, the population of the United States was about 308 million people. The national debt was about $17,547,000,000,000. And what we want to do is write each number in scientific notation, rounding the figures to 2 decimal places. And from those numbers, we would like to turn around and find the amount of debt per U.S. citizen. And we want to write the answer in both scientific and standard notation. Let's start with the population of the United States. The population of the United States is 308 million. So to write this in scientific notation, I would write 3.08. I'd put a decimal point just to the right of the first non-zero integer. And then it looks like I'm sliding the decimal point a total of 8 places. So times 10 to the 8th. Now the national debt, that was $17,547,000,000,000. So again, I'll put a decimal point to the right of the first non-zero integer. I have 1.7547 before my zeros kick in, times 10 to the, and then I count the number of spots that I would move the decimal point starting with the 7. So that'd be 3, 6, 9 for the zeros, 3 more, 12 for the 547, and 1 more for the 7, 13. So times 10 to the 13th. Next, I want to find the amount of the debt per U.S. citizen. Well, if I'm looking at debt per divide by U.S. citizen, I'll divide the debt by the number of people. And it's a whole lot easier to do without managing the zeros. So I'll have 1.7547 times 10 to the 13th divided by 3.08 times 10 to the 8th. This is much more manageable to do. Since I'm dividing, I'll divide the numbers that are not written where we have 10 raised to an exponent first. So I'll take 1.7547 divided by 3.08 and multiply by the quotient of, and now I'll turn my attention to where we have 10 raised to an exponent, 10 to the 13th over 10 to the 8th. Let's go to the first quotient. 1.7547 divided by 3.08 is 0.57 times, and when I divide with similar bases, I can subtract the exponents. So I have 10 to the 13 minus 8, that's 10 to the 5th. To write this in scientific notation, what do I need to do? Well, to write it in scientific notation, I'll put a decimal point to the right of the first non-zero integer. So I have 5.7 times 10 to the, now I made that number larger, so I'll have to make the exponent on the 10 smaller to compensate. So times 10 to the 4th. I'm going to go ahead and underline that. That's answering the question in scientific notation. Now let's answer the question so that we write the answer in standard notation. So I'll go ahead and write the 5, and I'll slide the decimal point 4 times to the right. I'll write the 7 with 3 more zeros. And it looks like our national debt was $57,000 per person. Thank you.